Okay. So welcome to the 9th class of Big Data Analytics, right? We covered, from day one, the concept of data and what do we mean by applying analytics. And again, in our class, I kind of grouped them into 3 parts. One is the interactive visualization. That means that if you can slice and dice and plot the data on the right axis using the right diagram, it immediately gives you the right insights that you can act upon. The second part is sort of like probabilistic modeling. That would mean, statistical inference. This is a more classical statistical approach to analyzing data, which means that there has to be some kind of assumption about the underlying data distribution. And the restriction is quite severe. It has to be, most of the time it's numerical data. A lot of time you have to assume things like normality, independence, and whatnot. And so it's quite not tedious, but it's quite a rigorous way of doing data analytics. But if you could do it, the result is very good because you can do all kind of statistical tests. There's very theoretical basis for all the tests, like tests for normality, tests for independence, all kind of stuff, and you can make very, very good conclusive statements about the statistical property and probabilistic behavior of your underlying population, of which the data is a sample, right? And then now we are on to the last part of the third group, which is that sometimes the pattern is not obvious. The data itself doesn't have very clear indication that you can apply statistical model. There's no presumption of normality or independence or all kind of nice properties. So what you do is you apply what we call machine learning techniques to it and see if you can infer some kind of insights from it, right? Now, from the whole of machine learning just simply means that you're kind of calibrating a model, right, based on data or some kind of quantitative figure, right? Now, I mentioned, I think I'll say it again, I keep liking to repeat myself, that there are basically 3 main paradigms of machine learning. There's unsupervised learning. This is similar to what you did when you first open your eyes from, when you were an infant. You look around, you make association between your mom and being fed and so forth, and loud jarring noise with something smelly. I don't know. Okay, just make some kind of auto association between phenomena that you experience. You were not being told to group things together, but naturally you started to make some kind of association. Second thing is, of course, supervised learning, and this is where your mom, your dad shows you a banana and says a banana, shows you an apple, says an apple, and then picks up a third fruit and asks you to say what it is. If that fruit is also a banana, right? Not the same banana, but another one, also a banana, and you said banana, then good. That's a direct feedback, right? And if you see that fruit, but you say apple, then your mom say, no, that's not right. That's not the apple, that's banana, okay? So it's a direct, immediate, yes or no, correct, incorrect, okay? And then there is what I call reinforcement learning. This is sort of like learning behavior over time. If you know how to share your toys with your friends and not be selfish and not bully your classmates, then you are more popular. But if you're rude and you're not cooperative and you're not respectful to your peers or your teacher, then over time people will not like you. And this is sort of like reinforcement learning, kind of learning the input response kind of function that over time is rewarded or negatively punish. Okay, so that's why it's called reinforcement. It can be positive and negative reinforcement. Positive reinforcement is reward, negative reinforcement is punishment. But that's really not mostly for things like well, principally for training robots or autonomous vehicle or something like that. Okay, or also a lot of engineering problems. So it's not really that much relevant to our class. There is a third thing, kind of semi-supervised manifold learning, embedding learning. I might touch up a little bit because that has a lot to do with emerging area of things like large language model, generative AI, ChatGPT and whatnot. A lot of it has implicitly this kind of embedding learning. And there's also like a graph embedding later. But besides giving it a sort of like a quick talk, perhaps toward the end of the semester, the more technical stuff will probably be left to another class, a class in machine learning proper, or a class in artificial intelligence proper. Okay, so last week, right? Last week, we started with supervised learning. And again, the reason we start, right, we did supervised learning last class. The reason we did it is because a lot of you are familiar with in traditional statistics where you do regression, okay? So sometimes we'll loosely use the word regression, prediction, sort of like loosely together. The idea is that, again, your data comes in input-output pairs, just like picture of a fruit, and the output is the label, banana. Picture of another fruit, the output is another label, apple, right? So there's IO pair, there's input output. Okay, there's an input output. And the way the data is presented in Mathematica is always input with an arrow to the output, right? So that's one sample. Another sample is another input point to output, input point to output, input point to output. Okay, so and I didn't have specific homework or assignment for that, but I think what will happen is next week, you will have a bit more experience working perhaps with Colab, with decision tree model and the PA coming. Okay. But if you will recall, the major demarcation I made last week was what? First of all, I made the distinction between regression or prediction problem and classification, right? Remember that? This is very important. This is conceptual. This is something that's going to be on the exam and all that, right? So it doesn't matter what the input or the X is. You look at the Y. The Y is the output. If the Y is categorical, which means it either come from nominal scale or ordinal scale, okay, chances are you're looking at a classification problem. You want a label, okay? A label is apple or orange or cat or dog, or 1 being the most beautiful, 2 being the runner-up in a beauty pageant, 3 being a second runner-up in a beauty pageant, whatever, okay? And then we have another group of problem just called prediction or regression, right? The output is numerical. So the numerical value can belong to what? What kind of scale? Either interval or ratio scale, right? Okay. And I show extensively how to work with it using very simple function, right? So basically, so for example, I have the data, I prepared in input-output form and so forth, fine, right? And then once you prepare the data into input-output form, then we come to here, okay? So the main section that you should look at is working with, working with supervised machine learning, right? So you prepare the data. So this is this bit here, okay? So once you prepare this data, you have two kind of problem, right? So let's build a model. Okay, let's build a model. So if it's numerical output, right? how do you build the model? You have the input output. Okay, first of all, don't forget to partition into training and testing data set, right? So in this case, I haven't run this, so it's still blue, obviously. So I can highlight the whole thing, but run it, but never mind. So when I say predict, right, without saying anything, for a small data set, mathematics is just going to run through different predictor function. Okay, but for a more, I guess, detailed analysis, or once you're happy with the approach, you want to specify, for example, I want to specify that the method is a neural network. Okay, in which case, not only do I say predict this, but I say predict this with the method option. Okay, so this is something, by the way, this for a small data set, you actually have to do this on the exam, because it's I'm not going to give you something that takes 5 minutes to run. So you can build a predictor here. Okay, in this case, I don't specify anything. I think from this example, it picked random forest or something. I can't remember. Doesn't matter. Okay. Whereas this thing here, if I say the method is neural network, it is going to build neural network. Okay. So that becomes a predictor function. So the output of this is not a prediction, but a predictor model. So that when you put in the new input, it makes a prediction, right? Likewise, for classification, the function you use to build the classifier is called classify. Okay, so I just kind of do them sort of like together here so you can see. Likewise, if you don't specify anything for data so tiny, by the way, this is iris data. It's only got 150 data points, so it's very tiny. This is the sort of thing that will be used on the exam, obviously, because it's a tiny data set. But if you specify, for example, decision tree, okay, it's going to use decision tree method. Okay, right? So this is what you did. We did last time. Now, once we built, okay, it's going to try to minimize some kind of prediction error, so forth, right? But you actually want to see, and there are many, there's no, just like in regression, guys, in regression, sometimes you say, is the regression good? You look at the R square, but they're actually more than that. There are residual plot. There are many things of saying, is the model doing well? Did it do well? If not, so where, how, or with respect to which data? So there's a lot of sort of like performance statistics or performance criteria. So with Mathematica, instead of just measuring them one at a time, there is a builder, another builder. Instead of building a prediction function or build the classification function, it takes that model that you built, right? Test it on a data set. Most of the time, that would mean the test set that you haven't seen, right? And it's going to gather all the statistics, regardless of whether or not you want to look at it. Okay. And I think somewhere down here, I show you that for prediction or regression problem, there are like 30 performance metrics that you can look at. But mainly, what do you look at? You look at R square, maybe. You look at residual plot, right? You look at, so there's sometimes you want to say if this is the actual value, this is the prediction, and you want to see everything along the 45-degree line, right? And if it's all over the place, then you pretty much haven't learned anything, okay? But if it's very close to the 45-degree line, means it's giving you exactly the same thing that the data contains, okay? Likewise, instead of having this 45-degree lines, for classification function, you would tend to look at confusion matrix, right? That would be same thing, except instead of having a line, you would have like a cell, right? So out of the whole total sample, these are cats, these are dogs, these are rabbits, and how many times the model actually predict cats, dogs, or rabbits? Okay. In our case, I think that it was the flowers, right? The three different different species of iris. Now, if you recall, I actually picked this 2 example to show you, one of the very trivial case, predicting iris, predicting iris, you always get like 99% or maybe 100% correct. Okay, and but for predicting like a daily movement of a FX series, like a Thai baht or dollar baht or something like that, you almost predicting noise. So no wonder you really don't get any good accuracy. Okay, so when you look at that plot thing, you don't get the nice 45-degree line. You just get things as a spread all over the place. Yeah. Now, this is just happened to be the case I brought up. Sometimes the opposite happens. In classification, it's almost random. You can't tell what's what. But in prediction, you can predict very, very precisely, get very high R square and so forth, right? So it just depends on the data. And that's, by the way, what we mean by data science. We mean that there's a lot of experimentation. Okay, sorry, experimentation. It's but with experimentate, yeah, well, it's a kind of like a same thing with medical experiment. You have to test disease versus different kind of drugs, right? Now, just because one drug is bad for one disease, that doesn't mean it's terrible for all disease. Okay, that's kind of obvious. Well, same thing here. Same thing here. Just because, except with drugs, it's a precise chemical composition, molecular chemical description of the drug agent. But whereas here, it's not a precise value, it's an approach. So sometimes neural network works really well, sometimes it doesn't. Sometimes decision tree works very well, sometimes it doesn't. Okay, right? So even though, in different cases, decision tree and neural network, we have different parameters, I still consider them the same kind of model. Okay. So, whereas with chemical drugs, it has to be exactly the same chemical formula. Okay. So this is the classifier measurement. Now, I didn't cover one thing, which is called ROC curve. I might come back to it, but in the interest of time, I'm going to skip over that and go directly to today's matter. And today's matter is to actually go to unsupervised learning. Okay. So in my book, unsupervised learning would be chapter 5. Okay. In fact, introduction to machine learning as a whole is put in here. Okay, so the first section of this is I haven't written this part, obviously, so this is the introduction, but I've been speaking that to you quite a long while. Okay, so let's these are, by the way, when I have all the URL here, these are reference to the actual function that has basically the help page, right? Now in Mathematica, obviously, if you have the name of the function, you press F1, it will go to that. But I'm writing this for a general case. That's why there's HTML, okay? But it actually goes to the same page, exactly the same. So don't worry about it. So even if you don't have internet, if you have a Mathematica, you click on the name of the function, k-means, k-mean-doid, agglomerate, classifier, find cluster, and all that kind of stuff. You're still going to get to the help page. You don't need the internet, okay? But here I use the HTTPS, so no big deal. Right. Okay. So let's do a little bit of a hand waving. Okay, hand waving. Actually, better than that, let's do a little bit of hand drawn. Let me do this. Let me stop share here. Right. And I go to here. And I share screen. And I share this guy. Okay. Is that right? And I have to press here. Okay, that's for this. Okay. Okay. Remember last time, if your data is sort of like this, okay? And this has a label, I don't know, okay? Maybe this is X1 and X2, right? And this is some characteristic X1 and X2. And this one is cat. This one is dog. And this one is, I don't know, rabbit. Okay. The idea here is what you want to do is a function that takes in X1 and X2 and will give you either cat, dog, or rabbit. Okay, we drew this. I think I threw the paper away. Okay, you remember that, right? So this is classification. Okay, now you get something more numerical like X. Now this one, I'm just going to have one X because I want to draw in here. And you have something like this, okay? And you want to draw a line like this, and then you want to say f of X go to Y, okay? So you want to predict Y given just that one X. So this is kind of regression problem. Now, okay? Now, go back here again. Okay, you know this. Look at this problem. Okay, you can say that the label is what dominates the picture here. You know what a cat is, you know what a dog is, you know what a rabbit is. These are maybe physical measurement like height or weight or whatever associated with them. Okay, so it's very possible that cats and dogs, you know, a similar size. You're just not measuring the right discriminating factor. If you're measuring weight, chances are they're fat cat and there's tiny dogs. Okay, so in reality, you get something that's, you know, it's not. There's a lot of cats here. There's a lot of dogs. There's a lot of overlap. Okay, but when it's a thing, you know which ones are cats. You know which ones are dogs. Okay, what that means is that the data set comes in the form of X1, X2, cat, X1, X2, cat, X1, X2, dog, right? This is what Mathematica would look like, right? The data looks like this, okay? Definitely, this thing is something that you knew, okay? So cats and dogs definitely are different animals. You hope, very important here, that the X1 and X2 that you choose to measure will allow you to separate them clearly. Okay, that's called variable selection. Okay, so in my example, a cat and dog, if you just measure, I don't know, height and weight, that's probably not very good. Okay, but if you measure something like ability to catch mouse or something, I don't know, okay, or the length of a hair around the nose, okay, cats have long hair. Oh, sorry, they call whisker, not hair. Okay, so if you measure whisker length, that would be very different between cats and dog, right? But if you measure just the weight, that's not going to be very good. Okay, so label comes first. You hope you get the variable that would help distinguish them. Okay, that's your problem. Today is the opposite. Today, you actually have one population. Can you see? Okay. Let's say you have something like this. Okay. You can see that there are 3 clusters, right? 3 clusters. In which case, what you would like to say, the cluster itself is the name of the game. You don't have anything else. So what you would like to do is somehow create this clustering assignment so that you say this is cluster number 1. You're not saying cats or dog because you don't know what it is. There's no label. There's absolutely no label. Okay. And this is number 2. And this is number 3. Now, if I took the previous data set, cat, dogs, and rabbit, and hide the label, cat, dogs, and rabbit, you also get something like this, right? But that's not the way I want you to think about it, because the way I want you to think about it is that there's actually no fundamental reason why there should be 3 groups. This could be all human beings. The reason you want to characterize them as group 1, 2, 3 is because you're not using that to identify what kind of animal it is, but you're trying to identify the natural clustering of behavior. Okay? So For example, everybody here is a human being. Okay? X is the amount of time you spend sleeping. Okay? Y or X2 is the amount of time you spend taking a shower. Okay? There's absolutely no reason why there should be 3 groups of human beings. Okay? So in this case, the label doesn't come. There's no automatic label. In a way, and I hate to confuse you this is actually classification the way biologists used to do it. Okay? In other words, it's not identification. Remember I told you that in data analytics, when you say classification, you're actually doing identification. Okay? Whereas biologists, they actually classify, mean they actually put animals into groups. Well, this would be like that, except it's actually not different animals, not different species, same species. But I'm going to separate them according to behavioral species. This group is sort of like to sleep, not too long, not too short, but doesn't like to take a long shower. Okay? This group sleep long, takes long shower. Okay? This group doesn't sleep very much and takes a long take very long shower. Okay? So, 7 o'clock or 6 o'clock, wakes up, instead of staying in bed, just jump in and take another hour of shower. Okay, fine. Okay, this is natural. This is natural. This is an example of what we call unsupervised learning. The learning to label, quote unquote, into 1, 2, 3. Okay, now 1, 2, 3 has no name, not cat, rat, or a dog, or rabbit. Okay, you can give the name later. Okay, you can give a name later, something like, this guy would be like lazy. Oh, I don't know. I don't, that the name comes later. The names come later. Okay, but it's not the ground truth. The ground truth is the natural clustering. When you say clustering, that means that some groups of the population are close to each other with respect to X1 and X2. Now, here's very important, by the way, guys, very important. Just like you can belong to drama club and fencing club and swimming, somebody belongs to swimming club and cooking, right? That is entirely up to you. Likewise, you can see that based on this sleeping time and shower time, there are these groups. But if I want to take the same human population and I use another X1 and X2, okay? Say amount of time studying and amount of time exercising, okay? Maybe I would get 5 natural cluster, okay? Or maybe all bar-size students have just 1 cluster, study really hard, doesn't exercise, or I don't know, okay? So you may belong, two of you may belong to the same cluster when I measure you with respect to X1 and X2. But when I measure you with respect to X3 and X4, you may be very far apart. Okay? Okay. So that's the name of the game. That's the name of the game. Now, so this here is one, just like in supervised learning, there are 2 types of problem. You have classification, right? And regression or prediction. I use the word interchangeably in that context. So maybe prediction, classification. Okay, let's use those 2 words. Here, I also am telling you that in unsupervised learning, there are 2 types of main problem. This one is called clustering. Okay, this one is called clustering. Another one I haven't told you yet. Okay, now, okay, do you get the picture? Okay, so this is the name of the game. We'll go to Mathematica, show you how things are done, right? and how to build the function and all that. Okay, so this is the name of the game, right? Name of the game. Now, there are many ways of doing this. Here's where some students have a hard time relating to unsupervised learning. And sometimes that's why you probably teach unsupervised learning after you teach supervised learning, although, and that's not necessarily the reason why. With supervised learning, it's kind of obvious what you want the model to do. Because you have the right ground truth, you have the right why. If you get the right why, the closest, right? You see cat, say cat. You predict 35%, 35 inches of rainfall, and you predict 37 as opposed to 2. Okay, you are very close. So it's almost like a given that what you want to do is get to accuracy. Yeah. This thing here, it's a little bit hard. You have to have an implicit criteria. What does it mean? Okay, because if you think about it, if I inspect very closely, maybe instead of looking at this and I say, oh, there are 3 groups, maybe I can look here and say, oh, there's another group here, there's another group here. So why not 4 groups, right? It's not, there's no absolute. Let's put it this way. Now, I will give you what the criteria is, and this is very silly. If these were not human beings, well, human beings, but they represent your clients, and X1 and X2 represent different kind of behavior, then how many clusters would you want to have? Well, for practical purpose, I'm making a big joke out of this, but you can think about this in real term. What if I have 4 sales force or 4 salesperson, right? So my criteria for making this clustering is not, what does it look natural? No, not only do I want it to look natural clustering, I want to separate into 4 clusters, right? And hopefully the 4 clusters have similar number in each or something like that. Okay, so you can see why it's not hard and fast rule. Okay, clustering is a little, it's not anything goes. There's an objective to it, but it's not, it depends on application. Okay, there's no hard and fast rule. So again, a very good natural clustering may be 3 groups, but I have 4 person to divide this, right? I want to divide my client to 4 sector because I have 4 salesperson. Okay, now maybe it turns out that I have 3 groups and 1 group is really big, so I have 2 person in that group. Okay, maybe that works as well. Okay, the point is, it's not like in a regression or prediction problem where what do you want? Accuracy. End of story, right? So this is kind of like it's like there's no right and wrong way of organizing your desk. Okay, I can organize my desk so that everything is equal distance to my arm. That's one criteria. I can organize my desk so that things that I use all the time is closer, things that I don't use is further back. I can organize things my desk so that heavy things are in the middle so they don't get knocked over, and lighter things are, they're different criteria, right? That's what I want you to think about. Okay, it's not all nonsense, but at the same time, it's not hard and fast rule like accuracy wins every time. Okay. By the way, even accuracy, remember last time, even if the accuracy is neck and neck, what do I prefer? Simpler model, right? Decision tree over neural network. Simpler, explainable, not only simple, transparent, explainable. You can say which variable does what. Okay. So, and this is sort of like the art and science of it, Okay. Now, let me show you another thing which is really tricky. Implicitly, when I draw this picture, the reason I say that there are 3 clusters and you guys don't disagree with me, right? It makes sense, right? To draw three clusters, okay? Implicitly, what is your criteria for saying that things are clustered? Distance, right? Implicitly, things that are closer together belong to the same cluster, right? Right? Aha. Let me draw you another picture. Okay. You probably would not mind if I said there are also two clusters. Except how would I draw that cluster? I would draw one cluster here, and I would draw another cluster here. Wait a minute. These 2 points are far apart. These 2 points are much closer. How come I don't draw them in the same cluster and you guys don't mind? See? Now, am I ignoring distance? No, I'm using distance, except it's local distance. Data belong to the same cluster if you can get to each other small step at a time. Okay? Where would you see something like this? Well, I'll give you something very obvious. Bangkok, right? You take the map, there's a river, Chao Phraya, right? Runs here. Okay? This is Papadang. You know, you don't get to it. You really don't get to it. And if you analyze it like a property, say you're doing some kind of real estate model, you would definitely see that these guys have the same property value per square right or square meters. These guys have a very different valuation function. Well, this is actually proper dam. You have to go across the river. So that's why it's not contiguous. You don't get from here to here easily, right? But you can get from this house to this house. So if you have a friend, if you live here, you probably see this friend more often than this friend because this one is way out there, even though the distance is just here, right? You see what I mean? So that's a kind of analogy, right? By distance, I'm looking at you right here, but it's river, right? Whereas 2 miles down by foot, I can get to there easily. So in this case, yes, it's a distance, but it's more of a contiguous distance per step. Okay. Now, these two represent two different ways of thinking about clustering. I might as well give you the name. This global distance is called distance base or metric base. This one is based on density. Actually, they're both based on distance, right? But in terms of name, this is distance-based clustering and density-based clustering. Okay? So if you have a kind of contiguous mass, then it becomes this. You would the reason. Now here's where it gets tricky, and this is a little bit of a terrible chicken and egg analogy, right? How would you know if I should use algorithm based on distance, or how would I use, when would I use distance-based algorithm versus density-based algorithm? How would I know? Well, I would look at the plot, right? Unfortunately, that's not how life works, because if you can look at it, that means it's in two-dimensional. You don't need computer algorithm. Okay, so this is you know, you go to YouTube, you go to a data science class, you always see this picture. Okay, and you get this sense that, oh yeah, I know. If it's like this, I'm going to use density base. If it's like this, I'm going to use cluster base. The point is that if you can see it, you don't have to do any algorithm on it. It's two-dimensional. The point is that this thing is in 20 dimensions. Okay, so in real life, I can tell you it's this is not something that even the most experienced or the most advanced data scientists can tell you. Okay. You hopefully there's some kind of like, there's some kind of implicit thinking, like if X1 and X2 are kind of like this kind of well-behaved normal distribution kind of thing, then chances are use distance-based. Okay. But in reality, I can tell you, and I'm sorry to say this, no idea. No, I mean, no, not the right idea. You can't really tell right away. Okay. You can't tell right away. What you might do in real life, one thing is you might just say, well, how about if I plot, I have 20 dimensions, X1 to X20. I just plot at a couple of pictures, X1 versus X2, X2, X3, X3, X4, 5, 6, 7, you know, that sort of thing, to see if data kind of like have any kind of discernible pattern to it. Okay. But in reality, there's, you know, your guess is as good as mine. Okay. You know. Okay. So that's the problem. That's what you want to do, right? So in a way, you are giving a label where labels did not exist. Think of it this way. Okay. And you get to do that according to some criteria. And if it's happened to be practical, I have 5,000 students, 5,000 clients, and I have 4 persons who are my sales force. They can specialize in different behavior. If I can cluster it in 4 ways, right? And each of them roughly 1,250. Okay. So 4 way, that's 5,000. Okay. So everybody gets the same amount of job or something like that. Maybe, I don't know. Okay. So that's the sort of thing I want to do. Okay. That's the thing I want to do. Okay. Underline that. Okay. That's called clustering. Okay. Now, so go back to supervised learning again. Go to supervised learning again. Okay. Now look at the right-hand side. Look at the right-hand side. Okay. Look at the right-hand side. I'm going to make something even trickier. Okay. I'm drawing the right-hand side, but I'm making something even trickier. Okay. In this case, you know, you can't even make a regression function because it looks like an S, right? Right. Okay. Okay. Now go back to the analogy with the map again. Hey, wait a minute. If these are houses, and I'm a city planner, how would I build the road? I would actually build along that S. Does that make sense? Does that make sense? Now, once I've got a street address, what happens next? Well, I already said the word address, so you know. Address. Right? So if this is one road, this is house number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can literally organize the house along this curvy road. Okay? So now before that, you didn't have the road. You just have a whole bunch of points. Okay? But if you had the road, you can say, you know, the beginning of the road is house number 1, right? All the way to a house number 100. That's kind of nice. That's kind of nice. That's kind of nice. In fact, if I didn't have the road, how would you locate the person? I would have to get X coordinate and Y coordinate to tell you where the house is, right? Okay. Now let's say I'm going to be even more precise. The house are actually on the road. How many numbers now do I need to identify? 1. Let me say that again. Okay. So I'm going to draw another picture, and this one is a little bit even more artificial looking. So this is where the houses are. Okay. Give me an address. How many numbers do I need to give an address? How many? 2. Why? Because the house lives in 2 dimensions, right? So I need 2 numbers, right? I need number along here, and I need number along here, right? So by making a road, I'm actually creating a different axis that looks like this. And I only need 1 number. Okay, let me say that again. I had the original dimension, right? X1 and X2. If I want to tell you which house it is, how many number do I need? 2. X1, X2. Right? Because why do I need 2 number? The house exists on a 2-dimensional plane. But actually, if I draw myself a road, the road itself lives in 2-dimensional plane. But with respect to the road, you are actually just a marker. So this community of houses is actually a 1-dimensional community. All right? Every house has the neighbor to the right and to the left. Right? You guys see what I mean? Okay? So yes, potentially you have 2 dimensions. And house actually live on 2 dimensions. But if I draw this line, which itself is 2-dimensional, and I mark the house according to where you are on that road, with respect to this line, if I take this line and I stretch it, this community becomes a 1-dimensional community. Does that make sense now? Okay. Now, this is also because I never told you what the ground truth is, but somehow I came up with this line such that when I stretch it, I actually reduce house address to 1 number instead of 2. What kind of unsupervised learning am I doing? What kind of problem it is? It is called dimensionality reduction. Right? Because that's exactly what I did. I reduced dimension from 2 to 1. Okay? Now, in reality, when you do this with data, it's not exactly on it, but the variation, just a little bit above the street, a little bit below the street, behind the ditch, that doesn't really matter, right? Okay? So that is problem called dimensionality reduction. But once I take this line and I throw this line away, okay? They have a red pen? Never mind. Okay, but look at my hand, okay? I throw this line away. I throw this line away. I take this line and I stretch it. This is what it looks like. It becomes a 1 dimension. Okay. First of all, philosophically, 2 things just happen. Okay. You can, or 2 equivalent things you can say. You can say that there's actually only 1 dimension that's necessary to separate you from your neighbor. You don't need 2 numbers. Okay, just house number. But this is possible. The flip side of it is, this is possible because you didn't explore the whole 2 dimension. You're given the freedom to live on 2 dimension, but you actually don't. You just happen to live on 1 dimension. Again, to keep to the real estate analogy, do you see this happening? All the time. Here's a flat land. Do people live everywhere? You evenly distributed? No, they live alongside river because they can catch fish and they can, whatever. Okay. So you would see that, historically, by the way, right? Before people built roads, okay, you dig up, you dig up huts or, archaeologists. There's a flat land. Do archaeologists go like this? Like when they search for people in the sea, people who fell overboard and the helicopter looked for it, right? Do you look like this? Hey, let's find this. Let's find all the houses. Okay, evenly, 2-dimension. No, actually, there's a river that looks like this. Archaeologists would just walk down the river. Yeah, because people before roads were built, they just live along the river. They can catch now presumably they can catch fish. It's not like a alligator infested river. That's a different story. But okay, people live around the river. They don't explore the full 2-dimension. They get themselves just on this 1-dimension. It just happened this 1-dimension is embedded in 2-dimension. Okay, remember that word embedded? I said it earlier in the beginning of the class. That's the 4th machine learning paradigm, but we probably won't get to it. Okay, so that's it. That's it. You now know two types of unsupervised learning. Now, let me go now to details. Okay. So for that, we have to go back to by the way, today I'm also going to do sort of like what I did last time, which is to give you a half an hour, maybe 45 minutes to work on the data. So stop share. Okay, and now share with this mouse. Okay. Now, I just show you, right? I just show you that in clustering, there's X1, X2, right? Let me show you an example where you don't know what X1, X2 is. Let me just do this. Okay, and you can do this along as well. Okay, start your Mathematica. You don't need to do random seed, but I do it so that every time I hit enter, it comes to the same number. Now, random color is a function. Just comes up with color randomly. Okay, I'm gonna take 100 of them. So this is 100 random hues. Okay, so actually let's not do this yet. Let me do this. Okay. Okay. So if I don't silence it, it's gonna look like this. Okay. Random colors. Right? Random colors. Now, of course, I mean, you're smart enough to figure out that colors is actually 3 numbers, right? It's actually 3-dimensional. But let's just pretend you don't know it. You don't know this. And you do some kind of clustering on it. Yes, you did this when you were kids, right? You had like a pencil thingy, we'll call it color pencil, right? And you sort of like groups the green together and the red together, right? Even though they're not quite the same green, they're not quite the same. Okay, let's see if we can do this. Now, so instead of doing, so that's what I did. Now, grid is just a way of organizing. But what I did was to use this function, find cluster. That's it. Now, it's one of those things, again, where for small problem, you haven't done much study, you don't specify the method. So here, you don't even say your density base or distance base. You say, find me some kind of cluster. Okay? Oops. So there, I can erase some of it. Find cluster. Find cluster. All right? Yeah. I don't know why it's taking long. It should be a very short amount of time. Okay. Now, what it does, if I didn't put the grid just sort of like put them in the blocks, right? But actually, this is what ended up doing. It found altogether 6 clusters. This is one cluster. This is another cluster. This is another cluster. This is another cluster. So you can see that within cluster, they have similar hue. Okay. Now visually, you can verify that they are similar, right? So this is kind of like sort of like I don't know, magenta kind of hues. This is kind of like earth tone, right? It's kind of soil kind of thing. This is probably like a dust kind of thing, and this is kind of greenish, light, pale, right? Doesn't matter. Okay. So that's exactly how clustering analysis does. Now, in this case, you have found six cluster, right? And they're not the same size. Fine, doesn't matter. So if I did this again and I don't do the same random seed, I come up. If I did the same random seed, obviously, right? It's the same number. But if I don't reseed it, it's now moved on to a different random seed. I get something else. Okay. Running. Okay, in this case, only two. Let's try again. Let's try again. Every time I shift enter, it just re-randomize. Yeah, still two. Well, keeps getting two. Let's keep getting two cluster. Now it's got four cluster. Okay, fine. Okay, so you see what I mean, right? Now, this is sort of like giving the cluster, but if instead of finding the cluster, I want to do what I did, like what I did in regression, I built a cluster classifier. I would use this word, cluster classifier. Okay, the difference is the first one just find the cluster. Okay, the second one sort of like give it a name. That's why it has the word classifier, because it's like classifying, but it's actually give it a name like 1, 2, 3, 4. So in this case, get something like this. So this is my classifier. Yeah, so it's a function. The output is not the data set classified. Okay, so if I have a list of things, right, and I pass it to the function called find classifier, find cluster, it's going to have bracket, and then bracket for the first cluster, comma, bracket, second cluster, comma, however many cluster, and then fourth bracket. Okay, but in this case, what I have is a function. I produce a function called classifier function. See that? Now, this is automatic, right? Remember I told you this mathematical high level stuff, build you automatic, but you can get information about what it is. So what is it? It is, the input type is color. So it knows it is working with color, okay? Now, you can work with text, but just work with color first. Then you can notice that there's 1, 2, 3, 4, right? So it doesn't have the label, but because it came up with 4 cluster, it's just going to numerically assign. The first cluster is named 1. The second cluster is named 2. So classes 1, 2, 3, 4. So it's kind of like unsupervised learning, but ends up with a supervised label data, except the label came from the natural clustering. So if now I have this function, okay, I have this function, and I go to somewhere else, okay, and I put in, let's say, I put in RGB color, okay, and let's make something kind of purpley. Let's make it 0.7 red, maybe 0 green, maybe 0.7 blue, okay? RGB, red, green, blue. Okay, so what does this look like, by the way? Let's do it in 2 steps. Test hue equal to this, and then classify test hue. Okay, purpley, very purpley, it gives you class number 2. See if that makes sense. One, two, three, four. Oh, I call different times. So yeah. Actually, this clustering here, now this is one thing where, because I call this in separate instance, so the numbering is not the same. Okay, it's still the same kind of algorithm, so it still came up with 4. So anyway, so if I take this, all of this, okay, all of this, let's make this let's make it comma. Comma. If that works. Yeah, I should have done the grid. Hold on. Let me take out the word grid. I don't want to read. I don't want to what you call it, re-randomize. So I'm just going to run it here separately, right? Find cluster, and I don't use the word grid, so okay. So I take this. Oh, it's given 3. Now, if I take another one, this one, it's all going to give the same cluster number. You get what I'm saying, right? So if I did this, the number is arbitrary. Okay, it could be 1, 2, 3, 4, or 4, 2, 3, 1. But the point is that if it comes from the same cluster, you should get the same number. Okay, it just happened to call this one 1, the other one 3. Okay, but the number is arbitrary. Okay, because the way it's used, the data could be presented in any order, so it's just random. So does that make sense? Okay, so if I did this, and maybe one more time, let's take this guy. Now, it can't be 1, it can't be 3. So what is it going to be? It's going to be 2. Okay, in this case. So now, for those of you who are sharp, you realize that I run the algorithm without rerunning the seed. So the algorithm itself is random. Now, this is something I never told you this. The data is random, right? If you give this data to maybe I should have said this in the beginning of the class, actually. When you do statistics, like fitting beta 1, beta 2, if you give it the same set of data, you're going to get exactly the same coefficient. It's repeatable. It's repeatable. With machine learning, the machine learning algorithm itself is governed by randomness. Not all of them, some of them. So that if you give it the same data, okay, it may actually end up slightly different. It wouldn't be materially different. It would be slightly different. Okay, that happens. That happens. And this is this is something that I should have sort of like forewarned at the beginning, because machine learning is not based on sometimes it's based on what's called stochastic search algorithm. It's a deep, you don't have to worry about it. But let's just say that when I apply the neural network or cluster finding or all these kind of machine learning tools, exact same technique, if you run it twice consecutively, you might get slightly different result. Okay, don't panic. Okay, that happens. So that's why you would need to do the same control. That's why this thing like this function like random seed, I use it a lot. You can see in my textbook, I keep saying seed random, seed random, seed random, seed random. This way I can make sure that every time I run it, I start from the same randomness. Okay. Okay. So fine. That's it. That's an example. Okay. Let me go to another example. Now this sample is from, you remember this example data? Right? Example data. There's so many of them, and just statistics alone, there are like 100 of them. Oops. So many of them. So these are so there are many example data, and within the statistic groups are like, a whole bunch of them. Now, these are all different things, all right? These are the things that I said, if you're really lazy, you can use this for your term project. Anyway, the one I use, I think, is called let me try to see. It's this one, Old Faithful. Oh yeah. Who's been to the United States, Yosemite National Park? Old Faithful is a geyser or geyser, however you say it. I say geyser. Okay. Geyser is spout of water. Okay, spout of water. What happened is that the water is geothermally heated underneath, right? Normally it just stays underneath, but here there's like a cavity, so that the heated becomes steam, and the steam builds up pressure. And once in a while, the pressure gets too high, it shoots out. Now, it's not going to shoot out just steam. It shoots out water, it shoots out whatever, and becomes like a nice looking thing for a minute or so. Okay? So here's the thing. So I take this data set. You can do this. Type like I say, example data, open bracket. Now, I want statistic, but now I know I want Old Faithful. So I type in open bracket statistics. So this say go to old statistics and Old Faithful. Okay. Now, what I'm going to do is I download it as data Old Faithful. I put bracket around it, list plot. So it looks like this. Nope. I happen to say image size small, so let's make image size large. Okay. Right. Now, there's also a description. There's a description. I think if you put in description, what happened here is where's the description? Okay, you have to put in something like comma description or something. Yeah. Oops. Automatically, it should not go to text. It should go to command. So, Old Faithful, comma, something like description. Anyway, that I don't. There's some syntax here that I keep forgetting. It's in the example data page. Go to F1 to tell you how to use it. Okay. Anyway, the point is, because I've done this before, so I know what the description is. The axis here, X1 here is actually minutes. X1, X2 here is minute. Okay. The X-axis is how long the water show lasts. The Y-axis is how long you have to wait for it. Okay. What it means is that if you look at this data point, what this data point say is that you waited 80 minutes. Oh, second, sorry, my bad. Second. You waited 80 seconds for an explosion that lasts 3.25 seconds. Okay, so this is waiting time. This is show time, basically. Okay, now I like this very much. I like this data so much. I use it all the time because it demonstrates so many things about data science, even though it's a very simple data set. Okay. First of all, visualization. Forget about interactive visualization. There's nothing you don't need to do any kind of interactive thing. Okay. There's only one data set that's just, maybe if the data covers year, you can try different years, right? This is it. This is the whole bunch of times. So maybe this is just one summer. Okay. Now, because the Old Faithful is a geological phenomena, it doesn't change from year to year very much. So, so you don't need to do interactive like before industrialization. It doesn't matter. It doesn't really matter. Okay. But this visualization tells you what? Anybody? By the way, this is something I can ask you to do on the exam time. First thing first, roughly speaking, long show, long wait, right? Because it has an upward slope. Make sense? Make sense, right? Makes sense, right? Also, minimum, you never get consecutive show closer than say 40 seconds, right? So if it's finished blowing up and you drop your iPhone, you have about 30 seconds to run get it before you get blasted in the face with hot steam. Although actually you don't get to go that close, but you see what I mean, right? So definitely you don't get, maybe 20 seconds is safe time. Okay. So you can go close and get a selfie for 20 seconds. Okay. You pretty much guarantee that you're not gonna be burned for 20 seconds after the last one. Just make sure that it has finished. Fine. So you can make this. Now, what else can you draw? Conclusion. Now, think of it this way. You are a geologist. You try to get insight. Now, when I say data science, you get insight, you make money, you make profit. Here, you're just trying to get insight. What does this look like to you? A geologist would notice that there's a break between small cluster here and a large cluster here, right? As a geologist, you might hypothesize. Now, I'm not a geologist, right? I'm pretending. Just look at this. The insight it gives me is that maybe there are two cavities. There's a smaller cavity, takes a shorter amount of time to fill, but it also has less water. So you wait less, but once it empties, it only lasts like what? Up to 3 seconds. Okay. And then maybe there's a bigger cavity. Okay. That cavity, you have to wait a little bit longer to fill. Right? Not twice as long, but because of the volume, right? You don't, you can fill, you see what I mean? The volume of water. So even though you maybe you don't get twice as much volume, but the show lasts up to 5 seconds. So this here is what scientists do. Okay. In fact, to be honest, before data science was a thing, this was the primary way of doing science. You look at the data, you visualize it, and you formulate it. You don't run through any statistic first. So in this case, you build a model based on data observation, and then you can test it. Okay, you can test it. Now, in our case, fine. In our case, again, I like this data because it's so simple. First of all, it's already 2 dimensions, so nothing much to worry. And you can also see that it has 2 clusters, right? So if I did this, okay, if I did this, find cluster, and I ask for dimension or length, chances are I'm going to get 2. So we don't have to do that. Okay, so actually shouldn't. LEN. Okay, so this length applied to this is 2 because out of this, I think there are about 300 sample point. There'll be a bracket outside and there are 2 brackets inside. Now, when I use length and then apply like this, it just counts, right? Counts the first one and the second one. So actually there's 174 of this and 98 of the other one. Okay. Okay. Now, let's do this. Let's take average. Ooh, I don't know why it's not giving default as a mathematical function. Now let's try it. I'm really curious, right? So I know that this run for the first cluster and second cluster, right? Now let's say I'm gonna say something like mean. Okay. Now the first data point. Okay. First data point is show time, right? So show time mean first data point. Okay. And so, oh, the first data point is actually a wait time, not a show time. So the first the first group of 174 is the long wait. It's the 41 seconds. So in other words, the algorithm partitioned this into 2 groups. And if I apply the mean to one axis, it's going to say, well, you have to wait around 40 seconds. Hold on just a second. Okay. Not doing something right. Let's do this. Ah, okay. Okay, gotcha. Gotcha. Make it numerical. Okay, now that's better. Sorry. I know that this thing is, once I did this, yeah, this is what I get, right? So it's actually 2 brackets. There's an outside bracket, and there's a altogether 300 data point. Somewhere here, it is 174 data point, and then there's like an 89 data point. So that's what it looks like. Okay. So I'm going to apply mean to that, and I'm going to apply n to make it numerical. Oops. So the first cluster, which has 174 member, meaning 174 data point, okay, is one of those that lasts 4 seconds. Why is it not doing? Oh, sorry. Last 4 seconds and wait 80 seconds. So this is the first group. The first group of 174, wait 80 seconds, the show lasts 4 seconds. And then there's a 98 data point where you wait around 54 seconds and you see for 2 seconds. Okay. So this is what you can expect when you go to see. Most of the time, it's actually a long wait, but longer show. Okay. So it's about what? Almost 2/3, not quite. Something like that. Okay. Now, notice this is different, right? If I came up with this and I labeled this thing, if I label this thing small cavity, and I label this thing long cavity, then it becomes a classification problem, right? This one is the opposite. I don't start with the label. I start with the data. It just so happens that there's a natural clustering. There's a short wait, short show time, long wait, long show time. Okay, most of the time it's long wait, long show time. Okay. That is okay. So you can test any data set. So if I, okay, oh, so once, now this is to find the cluster, right? But if I want to use this cluster classification, I would not use the word find cluster. I would use the word cluster classify. So that's this guy. Okay. So I built cluster classify first. Yeah. Do this later. Yeah. I built cluster classify. Then I use it to classify three things. Yeah. Now, it classified two types. So it's going to give this one to class number 1, this one class number 2, this one class number 2. So obviously that's one class. So this is the short wait, short show. This is the long show, long wait. This is the long show, long wait. And again, numeric, it gives you information. It is. Now remember, when you build this, like I said, if you don't know and it's a small data set, you might as well not specify the method. The Mathematica being a high level language is going to try a few things. You know what it did? You know what it did? It went to try a few clustering algorithms, and you can see what it came up with. This is called Gaussian mixture. Okay. So you may or may not learn about Gaussian mixture as a method. Okay. You may learn about k-means. You may learn about something else, but this is what Mathematica decided. By the way, let's look at the previous one, the one with the color. Do you know what this Mathematica came up with? This is the method, DB scan. Now, I happen to know that DB scan is a density-based algorithm, okay? I also happen to know that Gaussian mixture is a distance-based, okay? But you didn't know this, and you don't have to because, you know, this is automatic for you. You know what a Gaussian mixture is? It's, well, you hear the word Gaussian, what do you think of? Mathematician names Gauss. You think of the word Gauss, there's a Gaussian function. Gaussian function looks like this. So Gaussian function is actually the normal distribution. So what they're trying to say is it's a mix of two or more. Gaussian mixture mean exactly that. The population is a mix of normal distributed random variable. In this case, it's bivariate normal. Why bivariate? Because you got two values. So you can see, right? Instead of having this one axis, you actually have two axes for the waiting time and for the show time, right? So this is kind of like a hill. And this is another hill because there are two hills together, mixed together. Each hill is normal shape or Gaussian. The best one that the Mathematica found was called Gaussian normal. Gaussian mixture. Okay. So Gaussian mixture is basically that. You don't have just one normal distribution, could be univariate and bivariate or multivariate, but you have a few of them and you mix them. So it's like a subpopulation, so to speak. And let me see if that makes sense. Now, okay. So just to show you, and this is not about this. This is going back to bivariate distribution, right? This is bivariate normal. Okay, so you can imagine that a Gaussian mixture means you have two of these. So you take one of these and you put it on top of this. You take another one of these and you put it on top of this. And you have a Gaussian mixture. Okay. Do you want to know what it looks like? Let's go further down, see what it looks like. Now it's a different, it's something like this. Now this one use a different parameter. Actually, what I should do is use the same data set. This one I just make it up. I just make up the parameter. You can see what I mean, right? It's a little bit like this. So this one looks like a Gaussian, right? Because when you look at the side, it has a Gaussian shape, Gaussian shape, Gaussian shape. Now let's make it large. So Wrong word. Large. Okay. So there's one here, there's one there, right? Now, if this were the case, the data is randomly generated. It's going to be very far apart. Okay. Now let me show you what if it's a different thing. If it's something like let me move this thing back down a little bit. Turn it down. Now this is a little bit trickier, right? You can see why there's a lot more overlap here, right? You can see that. See that? Now this is so you can imagine that instead of this being drawn up arbitrarily, I just use, well, I can do that. I can do this. I can do, what do you call it? Where's my data? Histogram 2D, right? Let me see if that works. I may have to format this. Why isn't it? Why did it default as a oh, okay. It's weird. Oh, because I'm in slide mode. That's why I default to this. That's why. Okay, so histogram. Right. Histogram 3D at data on Facebook. See what happens. See? See that? That. So there's a smaller population of short wait, short show, long wait, and long show. And this one is not nice. So let's make it a smooth histogram. Smooth. There. See that? That. That. So think about it. Smooth histogram and in terms of statistics. So this is almost now. I just told you that we're doing machine learning. We're not doing statistics. But machine learning sometimes goes back, but not sometimes, a lot of time goes back and borrow function from statistics. In this case, Gaussian distribution is a very useful one. So machine learning, even though I'm doing, this kind of a cluster analysis, it actually goes back and say, you know what? This one looks nice. This one looks almost like a classical distribution, this bell shape. So why not build two bell shape? Okay. So this is actually two bell shape. It looks like that. Right? See that? And you can see that in terms of volume, which one is a bigger hill? This one. Why is this one a bigger hill? Well, because from this data set, it's got 174 of them. This one is a smaller hill because out of nearly 200, it's only about a third of them. So this one is almost twice as voluminous. Okay, so that's it. That's it. Now, so this is exactly what you would do in, real life. Let's see how many. This is a little bit, again, this is where I get crazy. All right. I built a whole bunch. So now instead of 2 hills, what if I have 4 hills? Right. And I can move them in and out. So this is what I'm using. Okay. So you can see that here. Now this is a bit tricky. And this is my point. Okay. Look, from here, it looks like density based 2 cluster is best. From here, it might look like that. But just slightly different, you can see that, hey, actually it's 1, 2, 3, 4. So, it's a bit cheating because now it's 2-dimensional, I can tell, right? In real life, you have to make this kind of model building when you cannot plot it. Okay, again, life is hard. If you can visualize it, you're done. If you can't visualize it, that's where you have all these tools for it. Okay. So this is, I make all kind of stuff. So I do the same exercise, right? But this is kind of like data that I make up, and it's all kind of weird things, and doesn't matter. Okay. So now one of the things that you can do is some particular kind of clustering is called dendrogram. And this one is kind of nice because it sort of like gives you sort of like a tree. Let me show you what, yeah, it looks a bit like that. So there's some kind of like it's not always useful, but let's say I want to well, let's go back to that example. Let's say I have 5,000 clients, right? And I'm separating them by characteristic. And let's say I separate it and it looks like this. And instead of having 4 salesperson to begin with, I can design any sales team I like. So what I might, based on this, okay, and this is a little bit of a quick thinking, sort of like heuristic thinking. Well, it looks like maybe I should have 2 different sales approach. And I put maybe 3 people here and 1 person there, or something like that, right? Okay. So this is kind of like, this is so a way of organizing. So this is all the data spread out, but in this kind of thing. Now, what is cool about this, and I'm being very loose here. I'm being very loose here. It's almost dimensionality reduction. Why? Because original data is in 2 dimensions. By putting them along the dendrogram, I'm lining them up. Almost, not quite. Okay. I'm almost doing that. I'm almost doing dimensional reduction. And some people would even say it is, but I don't. Yeah. Might say it is. Okay. So that's, example here. And this is how you do cluster analysis. Now, let's take a few minutes break. I'll come back. I'll go to dimensionality reduction. Okay. I could have taken a break before this, but dimensional reduction is very tricky. It takes a long time. So I want to bunch a cluster analysis with the first part of the lecture. Okay. So let's take a 5-minute break.